Hello everyone, I'm Antrish Malik, enrollment number E19CSE379. I'm a third year student at Bennett University and I will talk about Secure Shell. So, what is SSH? SSH stands for Secure Shell, which is a protocol that provides authentication, encryption, and data integrity to secure network communications. SSH client and server applications are widely available among popular operating systems and they offer a secure communication between the server and client. SSH is a secure replacement for Telnet, since any data that is transmitted using Telnet protocol, including user credential, is in a clear text format and anyone can read it. So Telnet is not secure and that's why we use SSH. SSH encrypts everything and sends it from client to server and back. And that's the reason that SSH is more secure and why it should be used when a client communicates with the server or remote logins to a server. SSH comprises of three protocols that run on top of the TCP protocol. First, we have the transport layer protocol that provides server authentication and data confidentiality. The second is the user authentication protocol that authenticates users, and the third is the connection protocol that multiplexes multiple logical communication channels over a single SSH connection. In other words, there isn't only one logical connection between a client and a server, and everything goes through that logical connection. Instead, there are multiple channels created. For example, one channel is for one session and another one is for port forwarding and so on. Let's go through these steps involved in establishing an SSH connection between client and server to find out how things work. Since SSH runs on top of the TCP protocol and the requests start coming from client requesting to communicate with the server. So here are the TCP handshakes that we see. SYN, the SYN and ACK, and then ACK packets that are exchanged between the client and server to establish the TCP connection. As soon as the connection is established, the first step of SSH is called identification string exchange. So here, client constructs a packet in this format. SSH protocol version and software version and sends that to the server. Then the server responds back with its own identification string message. If we go to the captured packages on Wireshark and open this SSH protocol there, you can see that identification string exchange we have SSH 2.0, which is the protocol version, and the software that is used is PuTTY with the release 0.73. So that's the identification string that was sent from client. And if you look at the one that was sent from the server, it's in the same format. We have SSH and then the protocol version, which in this case is 2.0 again. And then the software and version. And the software on the server is OpenSSH version 7.1. The next step is algorithm negotiation, which means that both the client and server will negotiate to come up with the key exchange encryption message, authentication code, and compression algorithms. The client sends the key exchange initialization message where it tells the server about its supported algorithms. The algorithms on the client list are sorted in order of preference. So, the topmost algorithm on the list is the most preferred one by the client. Then, the server responds back with the same key exchange initialization message telling the client about the list of supported algorithms. Now, since this is pretty much done at the same time, both client and server are guessing these algorithms. So, if both have come up with the same algorithm after the exchange of these messages, then they move forward to the next step. Otherwise, the server picks the first algorithm on the client list if it is supported by itself. If both sides cannot come up with the same algorithm, then the connection fails and both disconnect. So the client cannot SSH to the server. And lastly, if everything goes well, then we move on to the key exchange algorithm. In this phase, both systems use a key exchange algorithm, such as Diffie-Hellman algorithm. Or when I used recently, it used elliptic curve Diffie-Hellman to calculate a secret key. Now, elliptic curve Diffie-Hellman is another powerful version of Diffie-Hellman. Elliptic curve is the set of points that satisfy a specific mathematical equation. So, in simple words, the key values that are used as input to your Diffie-Hellman algorithm are some points on that curve. So, the process begins by the client generating an ephemeral key. One is private that remains with the client, and the second one, which is a public key, will be sent to the server in a message called SSH Message Key Exchange Elliptical Diffie-Hellman Initialization. Now, I just want to emphasize that the public private key that I mentioned here are for Diffie-Hellman key calculation. Now, the server has been waiting for this message, and as soon as it receives it, it generates its own pair of ephemeral public and private keys, and then uses these keys plus the public key that it received from client in its elliptic curve Diffie-Hellman algorithm to calculate a secret key. The second thing that the server is going to compute is called an exchange hash. So first, let's see how the hash is generated, and then I'll explain why we need that. Now to generate the hash, the server is going to use the hashing algorithm that both client and server agreed on. So in my case, they both agreed on a SHA-2 algorithm. So here are the inputs to this hash. We have client's identification string. Remember, this is the one that the earlier client sent to the server when the client wanted to establish its SSH communication. That's the first input to hash. Then we have server's identification string. Then after that we have the payload of the client's key exchange initialization. That will be another input to this hashing algorithm. Then we have the payload of the server's key exchange initialization message. The server also has a pair of public and private keys. These keys are different from the one that we use in Diffie-Hellman. These are the host keys that the server uses in asymmetric algorithms such as digital signature and digital certificates. Now, the server's public key is also an input to the hash computation. Then we have client's ephemeral public key. This is the one that the client earlier sent to the server to be by using Diffie-Hellman key calculation. Then we have a server ephemeral public key again. This key is the one that the server using Diffie-Hellman key calculation. And last but not the least is the share, shared secret key. After creating this hash, the server uses its private key to encrypt or sign the hash. Now, the server creates the hash to prove a few things to the client. First, since the hash has the shared secret key which was generated through Diffie-Hellman algorithm, it proves that the server was able to generate this key based on the value that the client had sent earlier. The hash is also signed by the server. So, the server is authenticating itself to the client, and it's a proof of the position of the private key. Meaning, if the client can decrypt the message with the server's public key, that means the message was encrypted with the server's private key. And the hash also serves as the session identifier in each key exchange phase. So that's the reason that the server creates this hash out of those values that we just discussed. Then the server constructs a message called SSH message key exchange of elliptic curve Diffie-Hellman, and it adds the exchange hash in the reply. The host public key and the public key generated for Diffie-Hellman algorithm to this message and then sends that to the client. Now here, in our Wireshark captured packets, it looks like this. So this is the message that was sent from the server to a client. You can see elliptic curve Diffie-Hellman key exchange reply. Here is the message code, elliptical of Diffie-Hellman key exchange reply, and these are the values that have been sent to the client. We have key exchange host key. So this is basically the public key of the server that has been sent to the client. Then we have ECDH elliptic curve Diffie-Hellman servers ephemeral public key. So that's the public key for Diffie-Hellman key calculation that the server is sending to client. And down here we have key exchange hash that has been signed by the server, and all of these three are sent to the client as part of this elliptic curve Diffie-Hellman key exchange message. Now, once the client receives the message, it uses the server's public key as an input to Diffie-Hellman key calculation, in addition to its own Diffie-Hellman private and public keys to compute the secret key. Once the secret key is calculated, then the client generates the exchange hash from the same inputs as the server. So the same hashing algorithm is going to be used, and the same client identification string, server's identification string, payload of client's key exchange initialization, payload of server's key exchange initialization, the server's public host key, the client's ephemeral public key, the server's public key, and the shared secret key are going to be input to this hash. Next, the client verifies the public key of the server. This is done by using digital certificate sent by the server. If there was one or a local database of public keys, if neither of these exist, meaning there is no digital certificate signed by a certification authority, nor is a local database of the server's public key, then it's up to the client to go ahead with accepting the public key or not. Since the client is allowed to accept the key without verification, so when you SSH to a server, if you see any of these warning messages, that means neither of the verification method existed. So the top message that you can see comes from PuTTY, and the bottom one is the SSH that I use on my Linux machine to SSH to another Linux machine. Now, if you answer yes to these warnings, that means you are accepting the public key of the server. That means you are trusting that public key of the server. Now, the client uses that public key to decrypt the hash that was sent by the server and compares it with the one that it created earlier in the process. If these hashes are the same, then the server has been authenticated. Now, for the future communications, the server and the client are not going to use the shared secret key that was created by Diffie-Hellman algorithm. Instead, they are using that key as a base to derive six new keys. Two keys for encryption from server to client and client to server, two initialization vector keys for server to client and vice versa. These keys are random numbers that are usually added as input to symmetric algorithm. Just to make the algorithm more secure and make it more difficult to break the ciphertext. And two for the integrity from server to client and client to server. The end of key exchange is signaled by the exchange of SSH message new keys message, informing each other that all future messages are encrypted using these new keys. And if we look at our Wireshark here, here are these messages in Wireshark. You can see on the server here, right at the end of this key exchange reply, Diffie-Hellman key exchange reply, I have new keys. Right down here, I have SSH version 2, and you can see here message code, new keys, and then right after that, I have these SSH messages, new keys from client to server. And here I have these new keys that were sent from client to server. The final step is service request. So the client sends an SSH message, service request packet, to request for the user authentication from the server. And then the server responds back with SSH message service accept. And that's how the secure session gets established, and client can provide the credentials to log in to the server through the encrypted channel. And that's all for SSH. Thank you.